This is a review of Force 1, number 10. Now the concept of this problem was, you've got a boy and a girl, they're on frictionless ice skates, they're standing on a frozen pond, and they push off of one another. This is just like the game that Lorenzo, you and I played together where we tried to push each other off, right? Except we didn't have ice skates on. But this is the question of what would happen if we did, right? Or what would happen if we were out in space and there was no other forces on us? Well, let's think about drawing a free body diagram. Recall that you can draw objects as a dot and think about all the forces on them. So I'm going to just off to the side here draw a quick free body diagram for the boy. He's a dot. Does he weigh something? Yes. He's standing on the ice. Would the ice support his weight? Yeah, otherwise he'd fall through, right? So he weighs something. What do we call those forces from surfaces that support weight? That force has a name. It's the normal. Are those forces going to be in balance for the rest of this problem? How do we know this? He doesn't break through the ice, and it says they keep their balance, right? So if he doesn't fall down, that means gravity and the normal force are going to be in balance the whole time. Are there any other forces on him? Right, he gets pushed by the girl. Now, the way I've drawn it, do you see that the way he would get pushed by the girl would be this way? Do you see that that amount of force right there is the net force because all the other forces on him cancel out? So I can use that amount of force to calculate his acceleration. Now, if I did a free body diagram for the girl, so she's a dot, does she weigh something? Does she weigh as much as the boy? No, because she has less Twinkies in her. So I would make her force due to gravity a little smaller. Is the ice going to support her weight? Yes. It won't push up as hard as it did on the boy because it doesn't need to. It will just cancel her weight. Now, are there any other forces on her? The boy is pushing on her, isn't he? As we saw when Lorenzo and I played that game, you can't push on each other. If one person pushes on the other, then the other pushes back, right? Now, which way would the girl be pushed because of her interaction with the boy? To the left or right? To the right. And what would be true about this force that the boy gets from the girl and this force that's exerted on the girl by the boy? They are not balanced because they're not on the same object. Balanced forces can only be exerted on the same object. But the force is the same amount. Right, they have different masses, so they'll accelerate at different rates. But the forces are the same. So even though we only mentioned the 62 Newton force once in the problem, that's the force for each of them separately because they're pushing on one another. Notice that I made one direction negative. In this case, I made the direction the boy is moving negative. So the force on the boy is a negative 62 newtons, and the force on the girl is 62 newtons. Now, what else do we know about them from the problem? Mass. We know their mass. So do you see that with the force on the boy and the mass on the boy, kind of dividing the problem, everything on the left is boy, everything on the right is girl. Do you see that I could use the force on the boy and the mass of the boy together in an equation to calculate the acceleration of the boy? Now, when I do that, you should get something like 0.82 meters per second per second. Do you get something like that? Now, for the girl, her acceleration will be different because she has less mass. The force is the same. When you calculate her acceleration, what did you get? 1.3 something? This is still in meters per second per second. Now, up to this point, this problem has been a dynamics problem. We're thinking about all the reasons why they're accelerating. We're applying Newton's law. Which law did we apply? Newton's third law, right? When one object pushes on one thing, the other object pushes back. In fact, you should be open right now to this page. Let's read Newton's third law, but let's put in the boy and the girl in this problem. So Newton's third law verbatim says, if an object exerts a force on another object, then the second object exerts a force on the first, equal in magnitude but opposite in direction. But let's, instead of just object, let's use this problem and put what's in the problem. So if the boy exerts a force on the girl, then the girl exerts a force on the boy. Equal in magnitude, but opposite in direction, and that's why we made one of the forces negative. It's the same amount of force. That's what equal in magnitude means. But opposite in direction means one of the objects is going to be pushed one way and one of the objects is going to be pushed the other. Now, if you have them both positive, you think that after they push off of one another, they're going to end up going in the same direction, which doesn't make a lot of sense. All right. Now, are we done? No, because we've done a dynamics problem. We know the acceleration of each of them, but the problem actually asks for their final speed after some amount of time. So now you have a kinematics problem where you could use Vf equals a times t. We gave you how long the push lasted, so that's how long the acceleration will last. So you take this acceleration and you put it here. You take the time you know, you put it here, and you calculate their final speed. What do you find out? Who goes faster, the girl or the boy? The girl goes faster. Is that because she was pushed harder? No. It's because she has less mass. She resists being accelerated less. She's made of less stuff, so she's easier to get moving.